That's like the main equation, okay? But with this main equation, you can still not find the final velocity. So what you have to do is you need to make some isolations, which I already did for you. So what with this final velocity? As you can see, it is raised to the second power. As you learned in math, to get rid of second powers, what you do is you apply a square root, okay? So you apply the square root in both sides of the equation, and you can still have the same equality. This is exactly what I did to get my isolation ready for final velocity. Okay, so as you can see, where in what kind of situations are we going to use these formulas? For example, when the word problem tells you about a final or the velocity after an object over a certain distance. Okay? So what are you going to need for these type of equations or for this kind of word problems? You're going to need the initial velocity. You're going to need acceleration and, of course, displacement. Because as you can see, this equation is basically related to displacement. Okay, so displacement is, it must be a given. Now, sometimes, as you have noticed in physics, you're not going to use the main equation. You have to use some isolations. So here I got ready for you isolations in case you need to find the initial velocity, where the final velocity is given, acceleration is given, or displacement is given. Here is the equation in case you need to find the acceleration. What are you going to need? You're going to need the two velocities and the displacement. And in the case that you need to find displacement, this is the equation that you should be needing. You're going to need the two velocities and the acceleration. So the idea is that you identify the givens. That's the most important step in physics. Now, understanding or reading carefully the word problem in order to identify all the givens needed. So I'm going to show you a word problem. Word problem. Give me 1 second. Okay. So let's take a look at the first problem. It says, I'm going to show you like this so we can identify the givens. Okay. So it says, a person pushing a stroller starts from rest, uniformly accelerating at a rate of 0.5 or 0.500 meters over second squared. What is the velocity of the stroller after it has traveled 4.75 meters? So in this part, in this exercise, the first thing I notice is, okay, the question, okay, the requested question is, what is the velocity? So they're asking me about velocity, but not any type of velocity. It says velocity under the condition that the stroller has covered a distance already, okay? So with this question, you already identify the situation. You're gonna find velocity covering a distance. So remember, this formula is called final velocity after displacement, okay? So here it's like there are like keywords, okay? So yes, they're asking you velocity after a distance was covered. Now, the problem also is giving you some other givens, like for example, accelerating at a rate of 0.5 meters over second squared. Because it says accelerating, you understand that's the acceleration. And then there is another implicit given that is in words, okay? They're not giving you the specific value for that, but they're telling you in words. They're telling you.
Starts
From rest, okay? And as I told you many times before, this is very, very important to identify some things in physics. So start from rest means that the object initially, in this case, the stroller initially was not moving. If it wasn't moving, means
zero.
the initial velocity is going to be zero. Okay, so with all that information that we have, we can start by writing the data provided, the givens. Okay, I like to call them givens. I call them. So, because it says start from rest, remember here, there's another key word that is from. From means that is like coming from a position, okay? Coming from an initial something. From represents an initial condition, okay? Just remember that. So it says start from rest means that the initial velocity, initial condition for velocity, 0 meters over second. Now, uniformly accelerating at a rate of 0.5 gives me information about acceleration. 0.500 is the same as you just write a 5, okay? Meters over second squared. And then they're asking me the velocity. What is the
Always
velocity?
is gonna be the acceleration, even if it says uniformly.
Yes. That means there is a constant acceleration. I mean, that you know that distance of 4.5 meters, 75, sorry, in 4.75 meters, the stroller was moving at a constant acceleration, okay? The acceleration was the same in all this distance. That's what it means. Okay. Then it says what is the velocity of the stroller after it has traveled 4.75 meters. So they are giving me a distance, or in this case, displacement of 4.75 meters, and they're asking me to find the velocity because it says after, I know that after represents a final condition, okay? So that means that I'm going to look for the final velocity, and this is my unknown of the problem. So what equation am I going to be using? Remember that I gave you 4 isolations, okay? So which one is going to be useful? I'm gonna call them by letters. What equation am I gonna be using for this problem?
A.
A, okay? It's already isolated for BF, so I'm gonna be using A. So I say BF is equal to the square root of initial velocity raised to the second power plus twice the acceleration distance. Okay.
Means
So,
that 2 means that it's gonna multiply the acceleration, right?
yes, that 2 is a coefficient, okay? So it's gonna multiply the acceleration and the displacement. Okay, it's like a distributive property, but it's not going to change your answer too much. Just put them together. I mean, you can write it like that, or you can write it 2 times A times delta X is going to be the same. So now you just plug in the givens. Remember the initial velocity we know is 0. So we can just get rid of this part. And so we say now the equation is a little bit even more simple, simpler. 2 times A times delta X the acceleration, that is 0.5 meters over second squared, times delta X, that is 4.75 meters. Now I want you to look at this. You will multiply meters over second squared times meters. When you do that, if you have meters times meters, this is going to give you meters to the second power. Okay?
Square.
Squared. So let's see. BF is going to be equal to multiply everything. 4.75.
4.75.
Okay, so this is the square root of, I haven't applied the square root yet. Okay, so inside the square root you have the 4.75, but the units are different. Meters times meters are gonna give you meters to the second power.
4 meters.
And then below you're gonna have the seconds square, okay? So you just write it down.
Miss,
Yes?
I got a different answer in that part. I don't know why.
Because you probably applied the square root in the first place. Probably you did it like that. Now, remember, I do it step by step. But it makes sense. Take a look. How can we make sure we did it right? 2 times 0.5 gives you 1. And 1 times 4.75 is going to give you 4.75. Always try to make sure that what you get makes sense. Okay? A quick check, you can do it mentally even sometimes.
Means, and also to make sure to use the parentheses.
Yes, you can also make sure to use parentheses. But in this case, in your calculator, if you do that's what I'm telling you, apply the square root in the last step. Don't apply it first, because the calculator will interpret. So you have the square root of 2 times parentheses 0.5 parentheses 4.75. If you do like that, the calculator understands that the square root applies only to the first number. So I'm telling you, apply the square root in the last step.
I still got.
Did you get the 475 now?
No.
Just forget the square root, okay? Imagine you don't have a square root over there. Just pretend. Did you get the answer now?
Put 2 times 0.5 and after you put times 4.75.
Remember that between every single one you have a multiplication symbol. Did you get it now?
There doesn't count this.
Yes.
Okay, now yes.
Yeah, that was my mistake. The square there. Thank you.
Okay. Yes. So as I told you, just pretend you don't have a square root over there and apply it after. Now take a look at this. When you see this, I know that in the end, you're very practical, you're not gonna do this, but I have to explain it. This is also the same as having 4.75 inside a square root times just the properties of square roots. Just remember that. Meter square over second square. So what happens here? You have to get the square root of 475, but also the square root of the units. And this is also just this part, okay? Just this part is also equal to the square root of meter square over the square root second square. So what happens when you have this? You can cancel the square power with the square root. Properties of power, okay? The second power with the other square root. So in the end, just the units, you will have this final result, okay?
Only meters per second.
Meters over second. Does it make sense? Are you looking for velocity? Yes.
Yeah.
Okay, so it makes sense. That's all I'm trying to say. I know that I told you already, okay? That in the end, you're probably not going to do that in all the exercises. But I want you to understand where the units are coming from. It's all related to math, okay? So, once you know this procedure already, I'm gonna put it apart, okay? You can write it in your notebook once, okay? You can write it in your notebook once. And how much is this? What is the square root of 4.75?
2.18.
0.17.
2.18.
2.18.
179, you round it to 18. 2.18, and the units, remember what we got? We got meters over second. So we just write the units, meters over second. I know my students always say, oh, miss, let's just write meters over second. I know you're gonna do that. But I want you to understand that it comes from a procedure, okay? I didn't came up with the meters over second out of nothing. It all comes from a procedure that makes sense. Sarah?
Miss, what about the units? We're not going to write them like a fraction.
You can write it like that, or you can write it like a fraction. It's going to be okay. Both ways are okay. Now, I prefer to write it like this when I have to do a conversion. If I don't need to do a conversion, if that is my final result, I prefer to write it like I had before. But both ways are correct.
So in this case, you're writing it standard. Like standard.
I will say that this form is more standard for people to understand it. Like meters / seconds, it's more like common to use. Now, for conversions is, trust me, the fraction way is the best way to do it because you can see the location of every unit and you can cancel them correctly because that is like the most common mistake when doing conversions. So I'm going to call this procedure units procedure that I know you're probably not gonna do that, but it's very useful that you know where it comes from. Okay, that's why. And that's it. That's all you have to apply in that exercise. I don't know if you still have a doubt in any of these steps. The key, as I told you, is gather the information from the word problem. Just keep in mind the keywords from, after, okay? From means initial, after means final condition. And from that, you can organize the data in the way you prefer. Let's do one more example then. I'm gonna bring the formulas. So I'm gonna bring the formulas again. You don't, in your notebook, you won't need to write the formulas again, okay? I'm just, remember, this is my whiteboard. And this helps me a lot to, when I need to ask you something, okay? But you don't need to write the isolations twice. Now, in 1970, a rocket-powered car called Blue Flame achieved a maximum speed of 1 times 10 to the third power kilometers per hour, or 278 meters per second. Suppose the magnitude of the car's constant acceleration is 5.55 meters over second squared. If the car is initially at rest, what is the distance traveled during its acceleration? So, take a look here. It's very interesting because they are giving you a maximum speed reached, okay? Maximum speed achieved or reached, okay? That is 1 times 10 to the third power kilometers per hour. But the problem is also giving you information that 278 meters over second. The problem is already giving you the conversion. In this case, you won't need to work with a conversion process. I mean, from converting kilometers per hour to meters over second is not going to be needed. So that first given over here, you can write it like as part of your givens, but in the end, what are you gonna use? Remember that we use our data in meters per second. Belen?
Need to have the question that if in the problem there is a conversion, it doesn't matter if we do it, you know, as like a first step. Oh.
It doesn't matter if you want to do it to check if the exercise is correct, or if you just want to practice. It doesn't matter, okay? You can still do it. So we write the data, all the data provided. Tell me, what equation are we gonna be using? A, B, C, or D?
D. D.
Okay. So the problem is giving me it says a maximum speed. I'm just gonna call this D max, and then I'm going to define if it's final or initial. D max equals 278 meters over second. It says, suppose the car's constant acceleration is acceleration, okay, 5.56 meters over second squared. The car is initially at rest. What does this mean? Initially at rest. What is this?
Zero.
But zero what? VI or VI?
Meters over second.
Meters over
VI.
VI, okay, initial velocity, 0 meters over second. So Vmax is going to be final or initial? You already have the initial, so this one is going to be actually the final velocity. And then they're asking you, what is the distance traveled? If I want to find the distance, what is it? Is it delta X? Is it A? Is it VI or is it VF? What is this?
X.
Delta X.
So delta X is going to be unknown. What equation are we going to be using?
Letter D.
Letter D. Okay. So delta X equals VF to the second power minus VI to the second power over 2A. And my recommendation is that you please solve this part and then perform the division. Let's substitute by the givens. Remember, these are raised to the second power. And initial velocity, we know it's 0, so we can just write 0. Okay, in this exercise, when you plug in the givens, the initial velocity, which is 0, you can get rid of it, okay? So the final equation is going to be just v2 squared divided by twice the acceleration, okay? This is exactly what you have over here. 278 raised to the second power gives you 77,284. Now, meters to the second power is meters squared. Seconds to the second power is seconds squared, okay? And below you have twice the acceleration, 2 times 5.56. That gives you 11.12. Now these units are meter over second squared. Now take a look right here. In this part, you can cancel the second square in the top with the second square below. This is exactly what happened here. So what remains? Remains the meter square by the meters. So this is the same as having meter squares are meters times meters, okay? And below you have 1 meter. This procedure allows you to eliminate meters in the top with meters below. So the final unit, the only unit that remained untouched for us for that saying is meter. So the final answer is delta x equals 6,950 meters.